St. Paul, Virginia. My name is Dr. Kelly Lepo. I'm an education and outreach scientist at the Space Telescope Science Institute in Baltimore, Maryland. And today I'm going to talk to you about our infrared eyes on the universe, the James Webb Space Telescope. So today we're going to talk a little bit about how Webb came to be, why we want to study infrared light and what the heck infrared light is, exploring the universe with Webb, and a little bit about the telescope itself. So the James Webb Space Telescope builds on this legacy of telescopes in space. Here are 3 telescopes picked not quite at random. The Hubble Space Telescope, which sees the type of light our eyes can see, and a little bit bluer and a little bit redder. The Chandra X-ray Observatory, which sees X-ray light. I don't think any of you have X-ray vision, so it gives us a very unique perspective on the universe. And the Spitzer Space Telescope, which sees an infrared light, and it ended its mission in 2020. Each one of these telescopes gives us a unique perspective on the universe. It gives us some really cool pictures. So here, starting from the Crab Nebula, is an image in X-rays of a pulsar, which is the corpse of a massive star, and around it are spiraling all of these electrons which are emitting X-ray light. And you can see this really cool structure at the heart of the Crab Nebula. Then moving over one, we have the star Zeta Ophiuchi. And what this star is doing in this infrared view is it's plowing into the gas and dust around it, sort of like a boat plowing through the water, and it's creating what is known as a bow shock. That's heating up the gas and the dust around it. And then we have a visible light view of the Ring Nebula. And this is a dying star like our sun that's puffing out its outer layers in this very gentle death. And combining all of those views together, we have the antennae galaxies with X-ray, infrared, and visible light. And here we see in red the star-forming regions where new stars are being born, and then the bluish areas where normal stars are living out their lives, and then these little dots, which are X-ray light, and those are showing us the end stage of very massive stars, which are also very hot, and so they're emitting X-rays. But one of the most special and intriguing images to come from space telescopes is this image. This is the Hubble Ultra Deep Field. And this is equivalent to the Hubble Space Telescope staring at one patch of sky that's dark for about 25 straight days. It didn't actually take 25 days to make this image. It was built up over time, so it actually took a lot longer. But what we see here is mostly galaxies. So there are 2 stars in this image. Can you find them? I'll give you a hint. There's one in the upper left corner, and there's one in the bottom right corner. They're the things with the spikes on them. But almost everything else in this image is a galaxy. There are about 10,000 galaxies in this image. And with a little bit more information, we can arrange these galaxies from near to us to farthest away. And so one cool thing about light is that light takes time to travel. So nearby galaxies will have light that has a light travel time of maybe a few million years. And light that is farthest, the galaxies that are farthest away will have light that have been traveling for billions of years to reach us, all the way into the very first galaxies in the universe. So we can arrange a flip book of galaxies over time and study them using deep fields like the Hubble Deep Field. And you may notice something in this image. The galaxies closest to us look kind of familiar, like spirals and ellipticals. But as you start going back in time, things start getting weirder and redder. So that really gives us the question, what are the very first galaxies like? What do they look like? What are their properties? How can we observe them? And you can't quite do that with Hubble. You need a different tool. So we need to capture faint infrared light. And why is this? This is because the universe is expanding. And all these galaxies are moving away from each other as the space between them gets bigger and bigger. And if you happen to have light that's traveling between galaxies, it gets stretched by this expansion of space. And it gets stretched to longer wavelengths, and that means redder light. And soon the light from these galaxies gets stretched so red it becomes infrared light. And so we need a different type of telescope to see these very farthest galaxies that have had their light stretched the most. So here's an early concept for what was called the Next Generation Space Telescope and became the James Webb Space Telescope. Planning for this telescope began in 1989 before Hubble was even launched. And construction and testing went from about 2002 until 2021 this year. So that's one reason we'd want to study infrared light. What are some others? Well, I say the word infrared, maybe you haven't heard of this before. It's a type of light. So if we look at the different types of light, we can order them from bluish light all the way to reddish light. And we can start with the blue light that we can't see with our own eyes. That goes from gamma rays to X-rays to UV light to visible light, which our eyes can see. And then you can go to even redder and longer wavelengths like infrared light and microwave light and radio light. These are all different types of light. The fancy word you can see right here is called the electromagnetic spectrum. You can use that to impress your friends. But these are all just kind of different types of light. And Webb specializes in the type of light that goes from the orangey reddy side of the light that our eyes can see all the way into invisible infrared light. So why do we need different types of light? Well, it's because we get different types of information. So here's a visible light image of some meerkats and a freshwater crocodile. If you had infrared eyes, this is what they would look like. You can see the meerkats are glowing. They're glowing with a type of light our eyes can't see that's redder than red. The freshwater crocodile, not glowing as much. That's because the meerkats are warm-blooded animals, and the freshwater crocodile is a cold-blooded animal. So it's about the same temperature as the ground below it, and the meerkats are much warmer, so they glow more brightly in infrared light. Another cool trick of infrared light is it allows you to peer through the dust that's everywhere in space and even study the dust itself. So here are the pillars of creation. It's this very famous image of a star-forming region in the Eagle Nebula. And inside those dark, dusty pillars, you can see a whole bunch of stars if you look with infrared eyes. And if you look even farther into the mid-infrared, you get to see the dust itself glowing. And as I said, if you want to study the ancient universe, you have to deal with the fact that light that started off in ultraviolet and visible wavelengths in very distant galaxies gets stretched into the infrared. So let's explore the universe with Webb and see what kind of science we can do with our fancy new telescope. We'll start off by what I was building up to, discovering some of the very first galaxies. So right now, this is the record holder for furthest galaxy ever seen. We're going to see even farther things with Webb by taking deep fields, just like we did with Hubble. By staring at the same patch of sky for a really long time and seeing what's the farthest thing we can see. We'll also be able to study black holes and how they change over time, from the black hole in the center of our own galaxy to the black holes in nearby galaxies to black holes in some of the most distant galaxies. And we can see how those black holes influence the galaxies that they formed inside of and how they feed back and influence the stars and the gas inside of those galaxies. We can also study stars and how they live and form and die. So again, here's another view of a dusty star-forming area on the left. And on the right, we can see through the dust with our infrared eyes and see what's going on in these newly forming stars. We can also examine planets within our solar system, from everywhere from Mars outward So we can study the atmospheres of Mars and Jupiter and Saturn and Uranus and Neptune. We can study moons in the outer solar system and the icy rocky things like the Kuiper Belt and comets. Outside of our solar system, we can study planets around other stars. So this image is a little complicated. I'll explain it here. We have a star, and we've placed a disk in front of the star to block out the starlight because it's very bright. And around it, you see 4 faint dots. And those 4 faint dots are actually planets orbiting around that star. So we'll be able to do this with Webb, and we'll be able to look at planets around other stars. And it turns out that the contrast between stars and planets is greatest in the infrared because stars are kind of faint and planets are kind of bright. We'll also be able to understand the atmosphere of these planets. We'll be able to look at the starlight shining through the atmosphere of the planets, and we'll be able to figure out what the atmospheres of those planets are made of, or if they even have atmospheres at all. We'll be able to detect things like carbon dioxide and water and methane and see what those planets are made out of and if they're like the planets we have in our own solar system. So that's the Webb science. Let's talk a little bit about the telescope itself. Webb is a feat of engineering. We had some very ambitious science goals that I talked about, and we have ambitious engineering to support those goals. We have the largest mirror we've ever sent into space. We have all of this advanced equipment to align the mirrors and detectors to detect this infrared light and things to keep the telescope cool as it's in space. A little bit more about the Webb mirror. So the Hubble has a 2.4 meter mirror. It's about the size of a 1-story building. And to get the same amount of details in infrared light, you actually need a bigger mirror because of the properties of light. So the redder the wavelength, the bigger the mirror you need to get the same level of detail. And so Webb has a 6.6 meter mirror. It's made out of 18 hexagonal segments, which we can align individually using actuators, little motors on the back of the mirrors. Another trick that Webb can do is it can split the light. It can spread out the light into individual wavelengths into sort of a rainbow. And we can use that to look for signatures of different elements and molecules within the light. And not only can we use this to tell what things are made out of, we can tell how they're moving, how dense they are, and how hot they are. This is called spectroscopy. And a lot of Webb science is going to come out of spectra rather than images. So where will Webb orbit? Webb orbits at a point called L2, or the second Lagrange point. That's another fancy word you can use to impress your friends. It's a point where the gravity from the sun and the earth and the moon all balance. It doesn't actually quite orbit at L2, it orbits around L2. And why does it have to go out so far? Hubble is orbiting around the earth. Why does Webb have to go 1,000,000 miles away from the earth? Well, it has to go so far away because Webb needs to be cold. Remember those meerkats and how they were glowing in infrared light? And you and me and this computer I'm talking into, we're all glowing in infrared light. And if you want to observe something other than the telescope itself, you have to get Webb very cold so it won't glow as much in infrared light. So that's why it has to be so far away. And also why we have to have this tennis court sized sun shield to block the light from the sun and the earth and the moon and keep the science side of Webb and its mirrors very, very, very cold. And by cold, I mean something like -390 degrees Fahrenheit or -235 degrees Celsius, 40 degrees above absolute zero. So ridiculously cold. And the sun-facing side of Webb will be very hot. It will be something like 260 degrees Fahrenheit or 125 degrees Celsius. So there's a huge temperature difference between the hot side and the cold side of Webb, and that's made possible by this very thin but very big sun shield layer. And there's also an active cooler, sort of a fancy refrigerator or air conditioner that keeps some instruments on Webb even colder. So we can look to the reddest wavelengths of light. So you may have seen in the news that Webb is now in Kourou, French Guiana. That's where it's going to launch from. If everything goes well and the weather cooperates, the date is December 18th, 2021. And it'll launch something like 7 in the morning, East Coast US time. So get your pajamas ready and you can have a little pajama launch party very early in the morning on the 18th. And Webb has to fold up to fit inside of the rocket, and then it will unfold once it's in space in this elaborate unfolding sequence as it travels from the Earth to L2 over about the course of a month. And then Webb will take about 6 months to cool down enough so it's very cold, and all the mirrors will be aligned and all the science instruments will be tested. And after about 6 months, we're going to get the first images back from Webb. So exciting! Webb is an international collaboration, and it has been since the beginning. More than 120 American, European, and Canadian universities have worked together to build Webb. It's a collaboration between NASA, the European Space Agency, and the Canadian Space Agency. And researchers from 14 countries and 29 US states are part of Webb. So it's a large number of people have worked very, very hard, have spent their careers building this telescope, and we're getting ready to launch it into orbit. So I hope you are all excited for Webb's images and data and discoveries to start rolling in about 6 months after launch. Webb will capture light from the first generation of galaxies in the early universe. It will help us map how galaxies and the black holes inside of them change over time. It will study how stars form, live, and die, and help us explore distant worlds, planets inside and outside of our solar system. Thanks again to the organizers and St. Paul Elementary School for inviting me to give this presentation. If you want to learn more about Webb, you can follow us on social media. The handles on Twitter are @NASAWebb and @Space Telescope. On Instagram, it's @NASAWebb and @Space_telescopes. On Facebook, you can find us at facebook.com/NASAWebb. And there are a couple websites you can check out. WebbTelescope.org has lots of cool resources and news about the telescope. There's also jwst.nasa.gov and nasa.gov/web. So thanks again for having me. I hope you learned something. I hope you were inspired to learn more about Webb and maybe watch the launch. And to all the young people out there, I hope you consider a career in science or engineering, and maybe one day you can control a cool, new, fancy space telescope. Bye.